Hello students. In this lesson we're going to be studying the GD&T concept of runout, the GD&T characteristic of runout. Okay, our objectives for this chapter are: 1. Describe the two types of runout tolerances. Number 2. Complete an interpretation drawing showing how each of the runout tolerances is measured. 3. Apply both types of runout tolerances on circular features and face surfaces. Number 4, specify runout tolerances using common datum feature references. And number 5, limit the area of application for a runout tolerance. Number 6 would be apply a runout tolerance to a tangent plane. Number 7, apply a runout tolerance to a feature in an assembly. And then the terms we need to look out for here are circular runout, total runout, surface variation, axis of rotation, multiple or common datum features, tangent plane, and limited tolerance zone application. Okay, what is runout? Runout tolerances apply to surface variations that occur relative to an axis of rotation. So the tolerance specification defines the amount of runout variation that's permitted on a surface or a tangent plane. Okay, so there are two types of runout: circular runout and total runout. And as it says in the second bullet here, the type is indicated by the geometric characteristic symbol. Very important about runout. They apply only to surfaces. They do not apply to features of size. And then the tolerance is always expressed as full indicator movement. And runout tolerances are always applied at RFS, and runout datum references are always applied regardless of material boundary, and they must include at least one datum feature reference, but two are possible. Okay, so it's always RFS, always RMB, and it only applies to surfaces. It's very important. Runout. Runout tolerances can be applied to surfaces of cylinders, cones, spherical surfaces, flat surfaces, or any surface with a circular cross-section centered on an axis. Okay, circular runout is the surface variation that's allowable at each circular element of the part. The tolerance value for a runout tolerance is not limited by the size limits of your feature. And each measurement of multiple measurements are evaluated separately. Yeah, so what happens here is that, you're positioning this indicator over one of these circular elements. You're going to spin the part around, measure the full indicator movement here, and then we'll move it over to the next element and we'll rotate it all around, and then check the indicator movement there. And so that's what it means by each measurement of multiple elements are evaluated separately. And then the largest reading for all of those measurements will be the circular runout for the part. Okay, so this feature control frame for a circular runout feature looks like this. We'll have a circular runout, which is just one arrow pointing up at an angle. The tolerance here, and it's always RFS. There's no modifiers, and there's always RMB. It always applies regardless of material boundary. The diameter symbol is never included. That's because we're only applying this runout to surfaces, not features of size. And it's always applied RFS, always applied RMB, and you can have one. You need one, but you could have more datum features referenced. Okay, here's what it looks like with a common datum, where we have two datums used as one datum. That's called a common datum reference. And then here we have two separate datum references. So circular runout applied to a cylinder. Okay, it's checked by multiple separate dial indicators readings per feature. Okay, internal or features internal or external features can be used, and the surface control relative to the axis of rotation. So the tolerance zones apply along the full extent of the feature unless otherwise specified. Okay, so how do we apply the tolerance? Okay, in this case, this is on a model. They're just using a leader with a dot to apply the tolerance to the surfaces. This is a orthographic view. We have our datum, our axis of rotation datum, A here. That's 562. Again, regardless of material boundary. And then we're applying runout tolerances to this diameter here and this diameter here separately, and those are applied with a leader and a feature control frame. The other way to do that would be to take an extension line from that surface and apply the tolerance to that extension line. That's the other valid way to apply a runout tolerance to a surface. Now let's talk about non-cylindrical surfaces of revolution. Okay, in this case we're talking about a cone here. These runout tolerances are applicable if features included circular elements centered on an axis of rotation. And this cone does have circular elements as drawn here, centered about this axis of rotation. And variations are measured with a dial indicator perpendicular to that surface. So again, we are going to take this dial indicator, and at each one of these circular elements we are going to spin the part around and get full indicator movement. And then after we get all the individual measurements, then the actual the actual reading is the one that would be the maximum, had the maximum indicator, full indicator movement. And here we're again, we have another feature here. It's more like a spherical feature, and we fix the dial indicator at a certain position, and we spin the part around, and we evaluate these individual surface elements for runout. Now, we can also perform a runout check on a flat face. Okay, so in this case, again, we have our datum axis for rotation here, datum A, and then we have a runout tolerance applied to the back face of the part here. Okay, we also have a runout tolerance applied to the spherical surface here as well. Okay, so how we would check that is we would check this one separately from the other one. And really what we would do is place the indicator on this circular element and revolve the part around there and get an indicator reading at that circular element, move to the next circular element, spin the part around, and then see what the runout is. So it controls the amount of wobble, if you will, when the part rotates about its axis, and it does not control shape of the overall surface. It just controls the runout. Okay, that was runout applied to face versus. Now, here's how we would go about limiting the tolerance zone application. Okay, let's say we had this cylinder over here. We have this common datum. We have datum B and datum A. We're going to use those together to form a common datum reference between those two datums. But we only really need our runout tolerance to be applicable over this certain distance here. And this is going to be based on, how the part is used, how the designer sees this part being used. In some cases, maybe it doesn't matter what kind of runout you got over here on this side or over on this side, but in this particular design, we need to limit the runout within this certain range. And here's how we do that. What we do is we apply the tolerance here, but we're applying it to a chain line. And then we have basic dimensions here defining the limits of the application of the tolerance. Okay, so the basic dimension says, hey, from this end over to where I'm starting to measure, my runout is 300 thousandths, and then I have to hold this runout of 9 thousandths over this length here of 1.2, and the length is indicated with a chain line. So this is how we apply a runout tolerance to a limited zone of application. So I want to talk a little bit about the axis of rotation. Now, all runout tolerances must include one or possibly more datum feature references to establish the axis of rotation. Entire surfaces, partial surfaces, or by datum targets is how we should do that. Datum feature selection is based on manufacturing and inspection processes, and also the size and proportions and relative locations of the datum features. I'm going to stop this movie right here, and we'll pick it up on the next one with a one datum feature slide.